So, what does it really take for life to exist? We often imagine intelligent life as something highly evolved, advanced civilizations with spaceships, languages, and philosophies. But the first requirement for any kind of life, even microbial, starts with the same basic conditions. We're not just searching for little green men. We're looking for chemistry, for stability, for balance. To understand alien life, we must begin by understanding how life began here, on Earth. And what's the first ingredient? Liquid water. As far as we know, every life form on Earth depends on water. It acts as a solvent, a transportation system, a structural component of cells. Without it, life, at least as we understand it, simply doesn't happen. That's why, when scientists search for habitable worlds, they focus heavily on what's known as the habitable zone, sometimes nicknamed the Goldilocks zone. This is the sweet spot around a star where a planet is not too hot, not too cold, and water can exist in liquid form. Take Venus, for example. It's the second planet from the Sun, similar in size to Earth, but it's far too close to our star. The surface temperature reaches 864 degrees, 462 degrees, hot enough to melt lead. Any water it once had would have boiled away long ago, stripped from the atmosphere and lost to space. On the other end of the spectrum lies Mars, the red planet. It's just far enough from the Sun that water, if not underground, mostly exists as ice. Surface temperatures average around 80 degrees. 62 degrees, see? Any standing water would freeze solid. But Earth sits right in that narrow band of possibility, where oceans can form, clouds can drift, rivers can carve valleys, and rain can nourish forests. This balance has existed for billions of years, and it's what made Earth the perfect cradle for life. So when astronomers find rocky planets in other solar systems, and those planets happen to orbit in the Goldilocks zone, they get excited, very excited. One such discovery occurred in June 2004, when European scientists announced they'd found the smallest exoplanet yet, just 14 times the size of Earth, orbiting a star 50 light-years away in the southern constellation Altair. It wasn't a perfect twin of Earth, but it was promising. It may have had a rocky surface, which increases the chances of holding water and therefore life. This class of worlds is often called super-Earths, planets that are larger than our own, but still small enough to have solid ground and possibly habitable atmospheres. But here's the challenge. Most of our current detection tools favor large, Jupiter-like gas giants. These planets exert stronger gravitational tugs on their stars and block more starlight when they pass in front of them, making them easier to detect. To find true Earth-sized planets, we need more advanced tools, more precision, more patience. That's where the Kepler Space Telescope comes in. Launched by NASA in 2009, Kepler's mission was simple: to monitor over 150,000 stars, watching for tiny, regular dips in brightness that occur when a planet crosses in front of its star, a phenomenon called a transit. By measuring how much light dims and how often, Kepler could calculate the size, orbit, and distance of a planet from its star. This allowed scientists to estimate whether the planet might lie in a habitable zone, and whether its size suggested a rocky composition. In just a few years, Kepler discovered over 2,600 confirmed planets and thousands more candidate worlds. Among them were dozens of Earth-sized planets orbiting in their stars' habitable zones. These weren't dreams. These were data, evidence that planets like Earth are out there, waiting. But what if life doesn't look for water? What if it thrives in environments we once thought were impossible? That question has led many scientists to study Earth's extreme environments, places where life somehow survives against all odds. These organisms are known as extremophiles. They live in places that would be lethal to most known species. boiling volcanic vents, radioactive waste, deep ice sheets, and even inside solid rock. Take Mono Lake in California, for instance. The water is 3 times saltier than the ocean and contains high levels of arsenic, toxic to humans. Yet, microbial life thrives there. Or consider the permafrost in Alaska, where temperatures remain below freezing for thousands of years. Scientists have thawed out microbes frozen in ice for millennia and watched them spring back to life. Somehow, they endured, waiting in suspended animation until warmth returned. These discoveries have rewritten the rules of biology. Life, it turns out, is more flexible, more adaptable, and more resilient than we ever thought. And if life can exist in boiling acid, under crushing pressures, or inside rocks, then surely it could survive on an alien world. So where should we look? Some scientists believe the best candidates aren't just faraway exoplanets, but right here in our own solar system. For example, Europa, one of Jupiter's moons, is covered in a thick layer of ice. But below that ice, many believe, lies a vast ocean, kept liquid by the intense gravitational flexing caused by Jupiter's pull. Just as hydrothermal vents on Earth's ocean floors harbor thriving ecosystems, perhaps Europa's seafloor does too. Then there's Titan, Saturn's largest moon. It's the only moon in the solar system with a thick atmosphere, composed largely of nitrogen, just like Earth. Titan is cold, around 280 GeV, 179 degrees Celsius, but it has lakes and rivers, not of water, but of liquid methane and ethane. Could some form of exotic life survive there, using methane the way we use water? NASA's Cassini spacecraft spent over a decade studying Saturn and its moons, revealing Titan's surface in unprecedented detail. And upcoming missions, like Dragonfly, a rotorcraft lander, aim to land on Titan in the 2030s to search for organic chemistry and perhaps signs of life. These aren't science fiction missions. They are real, funded, and in progress. And they reflect a growing realization in the scientific world. Life may not be rare at all. It may be common. It may be everywhere. So we ask again, what does it take for life to exist? A planet that's just the right size, in just the right place. A source of energy. A stable environment. And maybe, just maybe, the right spark. And if it happened once here, could it have happened 1,000,000 times out there? At Infinity Beyond, we believe the answer is yes.